Welcome back, everyone. Get ready for a really eye-opening explainer today. We're going to be looking closely at gas turbine generators, and honestly, we're tearing apart a massive engineering pitfall. We are talking about the shocking gap between the shiny, perfect promises a factory makes and the gritty, physical reality of generating power out in the field.
So let's just jump right into it with a mathematical mystery. Picture this. You buy a newly minted 5,000 kilowatt turbine, but when you actually plug it in and turn it on, it only delivers 4,188 kilowatts. I mean, that's a massive discrepancy, right? Where did the rest of it go? We're going to solve this step by step through a continuous process of deduction.
Well, to really understand why this happens, you have to transport yourself to a harsh, demanding environment. Imagine it's 2 a.m. on an offshore platform, a floating production storage and offloading unit, way out in the Gulf of Mexico. It's 35 degrees Celsius, and the humidity is just sitting at a sweltering 100%. You can literally feel the deck vibrating beneath your feet because this turbine is running at 3,000 RPM. It's the absolute beating heart of the power system, burning wellhead gas to produce every single watt of electricity on board.
But here's the catch, and it all starts with the ISO rating. This is the official nameplate factory rating of the machine. Honestly, think of it exactly like a new car's MPG rating. You know how the dealership boasts you're going to get 40 miles to the gallon? But you know that's a number calculated in a perfectly controlled lab, driving smoothly without ever touching the brakes? It's rarely what you actually see in daily stop-and-go traffic. The ISO rating on heavy industrial equipment is exactly the same concept.
See, for a turbine to hit its absolute maximum nameplate power, it demands a practically utopian laboratory. We're talking sea level altitude, exactly 60% relative humidity, a highly specific reference fuel, and crucially, an ambient air temperature of exactly 15 degrees Celsius. And this perfectly illustrates our core problem. If we look across the globe, we have to contrast that utopian European laboratory, which is basically a crisp spring morning, with where these machines actually live and work. As we jump down to the tropics, to offshore platforms popping up in West Africa, Southeast Asia, or our incredibly humid Gulf of Mexico scenario, we see the real conditions. Those perfect 15-degree ISO conditions, they practically never exist where industrial power is actually needed.
Which brings us to our first major power loss, the temperature penalty. Think about what happens as the ambient temperature climbs from that 15-degree baseline up to a sweltering 50 degrees. The output power just progressively plummets. Why? Because gas turbines breathe air, and hot air is less dense. The engineering rule of thumb here is absolutely critical. For every single degree Celsius rise in ambient temperature above that 15-degree ISO baseline, the turbine's power output drops by 0.5 to 0.8%.
So let's actually run the numbers and make this abstract math completely tangible. If we have a hot 40 degrees Celsius day on our offshore platform, we have to subtract the 15-degree baseline. That leaves us with 25 degrees of excess heat. If we multiply that by an average D rating factor of, say, 0.65%, we get a massive 16.25% reduction in total power output.
Bam! Just like that, we hit a dramatically new physical reality. We take our promised 5,000 kilowatt machine, apply that 16.25% temperature penalty, and suddenly our shiny, expensive turbine has shrunk to just 4,188 kilowatts. I mean, that is a massive hit just from the weather alone.
But hold on a second. Where does the rest of the power go? Because what we just calculated only accounts for the ambient air temperature. It's time to shift gears from environmental penalties and look at the sneaky, hidden mechanical and electrical losses hiding inside the system itself.
Because the physical realities definitely don't stop there. Engineers have to apply a brutal rule of thumb to account for unavoidable friction and degradation. Look, as a turbine runs, it gets dirty. Combustion deposits contaminate the engine. Lubrication oil becomes less efficient. Soot builds up on the blades. That dirty engine reality? That costs you about 5% of your power right off the top. Then, as the physical force moves from the spinning turbine through a speed-reducing gearbox, mechanical friction eats another 1.5 to 2.0%. And finally, the generator itself isn't perfectly efficient at converting that mechanical rotation into electricity, so you lose another 2 to 4%.
Now this is where it gets kind of punishing. These inefficiencies don't just add together, they multiply in a chain. The power degrades sequentially, creating a cascading effect. Step 1, the basic thermal efficiency of the turbine itself is only about 0.32. Actually, the reason for that is roughly 50 to 60% of a turbine's gross power goes straight back into driving its own air compressor. Step 2, the gearbox operates at 0.98 efficiency. In Step 3, the generator operates at 0.97 efficiency.
So when you want to find the overall thermal efficiency, from the fuel all the way to the electrical terminals, you have to multiply these factors together in a chain, 0.32 times 0.98 times 0.97, driving our total down to 0.304.
Which brings us to the climax of our reality check, 30%. Yeah, you heard that right. After all the mechanical friction, the electrical conversion losses, the environmental penalties, and the inherent thermal limits of the combustion cycle, the actual overall thermal efficiency of the entire system is a mere 30%.
So why are we digging into all these numbers? Why does this matter? Because this is the absolute core of an electrical engineer's purpose. When designing a power system, engineers must drastically overspec the equipment to survive the real world. If you need 4,000 kilowatts of power to keep an oil platform running, you simply cannot buy a 4,000 kilowatt ISO-rated turbine. If you fail to do this cascading math, you are going to end up with overloaded generators, plummeting system frequency, and ultimately, a catastrophic platform blackout.
Which leaves us with a pretty wild question to chew on as we wrap up our explainer today. If the overall efficiency of these massive, roaring industrial machines is only about 30%, how much total fuel is truly being burned and wasted as exhaust heat just to squeeze out that final megawatt of usable electricity to power the platform? Think about the sheer scale of energy required simply to overcome the realities of physics in the environment. I hope peeling back these layers really helped clarify how engine ratings actually work in the field. Thanks for learning with me today. And remember, always question those factory numbers.